Hello students of class 10. Today I am going to start arithmetic arithmetic of integers arithmetic of integers chapter chapter 3. Now at first, an integer an integer, this is class 10 advanced advanced mathematics advanced mathematics. An integer a is said to be divisible by an another integer is said to be divisible by an another integer b not equal to 0 if there exists an integer c such that a equal to bc, and in this case we say that b divides a, and in and is represented as and is represented as represented represented as and is represented as b divides a. So in this case we say that b divides a and is represented as b oblique a. B divides a. That means if b divides a, then a is equal to bc, where c belongs to integer z. Say c belongs to any integer z. And the elementary properties of divisibility, these are very important. Elementary properties of divisibility this is very important. First is the theorem 3. Let a, b, c be any three integers then first a divides 0, 1 divides a, and a divides a. Now second, a divides 1 if and only if a is equal to plus minus 1. Now third, if a divides b and c divides d, then AC divides BD. So see the proof. A divides B, that means B is equal to AR, where R belongs to integer, some integer multiple. Again, C divides B. What does this mean? That is D is equal to CS, where S belongs to some integer. Now, we multiply these two equations, this equation and this equation, we multiply. We get BD is equal to AR into CS. So BD equal to, I can write AC into RS. This RS is an integer. So this can be written as AC divides BD. This can be written AC divides BD. Now again, property 4. if A divides B and B divides C, then A divides C. So see here, A divides B, that means B is equal to AR. R belongs to some integer. B divides C, that means C is equal to BS. S is some integer. Now here C is equal to the value of B I can put here. This is equal to AR into S. Now see, C is equal to A, RS is some integer. So I can write that A divides C. So I can write A divides C. Now we are going to 5. A divides B and B divides A. This is possible if and only if A is equal to plus minus B. Now 6. If A divides B and B not equal to 0, then modulus A less than equal to modulus B. And the last property is see, if A divides B and C divides A, then your A divides Bx plus Cy, where X and Y are any integers. They are any integers. Now see one thing here. A divides B. So we can write B is equal to AR. R is some integer. C divides A. So we can write A is equal to CS. S is some integer. Because both R and S belongs to some integer. Now here we multiply this both side by x. Bx is equal to ARX, and here by we multiply this and A is equal to if A C belong one thing there is I made a mistake, so a problem has created. Here I have done it. This is A divides B and A divides C. A divides C. So A divides C. A divides C. So C is equal to AS. Now this is correct. I multiplied this both side by x because it is bx. So I multiplied this both side by x and this both side by y. Cy is equal to ASY. Now this equation and equation I added up. So bx plus cy is equal to arx plus asy. Now bx plus cy is equal to a common. Now see one thing. Here I have done a mistake. There is no r, only s. ASY. So a common, rx plus sy. So here you see this is some integer. Means we can write this rx plus sy belongs to some integer. So we can write a divides bx plus cy. This is the about divisibility, how it is represented, and the elementary properties. This is very important. So it becomes very easy for you to solve the exercise. So this is very important. Hello students of class 10, Advanced Mathematics. Advanced Mathematics. Chapter is Arithmetic in arithmetic of integers. Your chapter is arithmetic of integers chapter 3. Now see exercise 3.1. Here it is given that using method of mathematical induction so that first 1 plus 3 plus 5 plus dot 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 plus 2n minus 1 is equal to n square, where n belongs to natural number. So we start like this. Let solution, let Sn such that 1 plus 3 plus 5 plus dot 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 plus 2n minus 1 n square means Sn we are representing this statement as Sn. We are representing this statement as Sn. So at first we go for S1, and here 1 square, this is 1, and see the first term is 1, so S1 is true. Now we go to Sk such that 1 plus 3 plus 5 dot dot the statement 2k minus 1 is equal to k square. Let Sk, your Sk be true. Let Sk be true for n is equal to k, where k is a given natural number. Now Sk plus 1 plus 3 plus 5 plus dot 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 plus 2k plus 1 minus 1 equal to k plus 1 the whole square. Now I will move from the left hand side, that is 1 plus 3 plus 5 plus dot 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 plus bracket 2 k plus 1 minus 1, and preceding this term is this one, so 1 plus 3 plus 5 plus dot 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 plus 2k minus 1 plus 2 bracket k plus 1 minus 1. Now this value we know this is k square, so this will be equal to k square plus 2k plus 2 minus 1, so this will be k square plus 2k plus 1, and this is k plus 1 the whole square. This is equal to right hand side. See, this is right hand side, and at last we have to write a statement as k plus 1 is true whenever Sk is true. This is finished. Now I am going to another question. Another question, that is question number 2. Here again, 2 plus 4 plus 6 plus dot 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 plus 2n is equal to n plus 1, where n belongs to natural number. So let us take this statement. It will be, we are going to represent this statement as Sn. 2 plus 4 plus 6 plus dot 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 plus 2n equal to n plus 1, n belongs to natural number. So at first we are going to try for 1. So for 1, this is 1 into 1 plus 1, this is equal to 2. See, the first term is 2, so therefore S1 is 2. S1 is 2. Now we are going to Sk here. 2 plus 4 plus 6 plus dot 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 plus 2k, that is equal to k plus 1, k plus 1. Now let Sk be true, let this be true, for n is equal to k, where k is a given natural number, Now we are going to Sk plus 1, 2 plus 4 plus 6 plus dot 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 plus 2 bracket k plus 1, this is equal to k plus 1, k plus 1 plus 1. So now again I am going to move from the left hand side, that is 2 plus 4 plus 6 plus dot 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 to k plus 1. The preceding term of this is this 2k. So this will be 2 plus 4 plus 6 plus dot 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 plus 2k plus 2k plus 1. Now this value is k into k plus 1 plus 2k plus 1. So this will be k square plus k plus 2k plus 2. So this will be k square plus 3k plus 2. So we can write, splitting the middle term, k square plus 2k plus k plus 2. This will be k common, k plus 2, again 1 common, k plus 2. So this will be k plus 1, k plus 2. Now I can write k plus 1, k plus 2 as k plus 1 plus 1. So this is equal to right hand side. So when therefore as k plus 1 is true whenever as k is true. Now this is over. I am going to another question. That is question number say 5. Here 1 cube plus 2 cube plus 3 cube plus dot 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 plus n cube is equal to n plus 1 by 2 the whole square, and n belongs to natural number. So here again I am representing this statement as Sn 1 cube plus 2 cube plus 3 cube plus dot 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 plus n cube is equal to n plus 1 by 2 the whole square, where n belongs to natural number. So first of all I am going to try for 1. So here 1 into 1 plus 1 by 2 the whole square, this is equal to 2 by 2 the whole square, this is equal to 1, which I can represent as 1 cube. So my first term is 1 cube, therefore S1 is true. Now I am going to Sk 1 cube plus 2 cube plus 3 cube plus dot 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 plus k cube, and this is equal to k plus 1 by 2 the whole square. Now let Sk be true. Sk be true. So we are going to Sk plus 1. This will be 1 cube plus 2 cube plus 3 cube plus dot 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 plus k plus 1 the whole cube. This will be k plus 1, and again k plus 1 plus 1, that is k plus 2 by 2 the whole square. Now I will move from the left hand side, that is 1 cube plus 2 cube plus 3 cube plus dot 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 plus k plus 1 the whole cube. The preceding term of this is this. So 1 cube plus 2 cube plus 3 cube plus dot 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 plus k cube plus k plus 1 the whole cube. Now value of this is this. So this is k into k plus 1 by 2 the whole square plus k plus 1 the whole cube. So this becomes k square k plus 1 the whole square by 4 plus k plus 1 the whole cube. Now I am going to take the LCM. K square k plus 1 the whole square plus 4 k plus 1 the whole cube. So this becomes k plus 1 the whole square bracket k square k square plus 4 k plus 1 bracket close. This is k square bracket close by 4. So this becomes k plus 1 the whole square. Now k square plus 4k plus 4 bracket close by 4. So this will be k plus 1 the whole square, k plus 2 the whole square by 4, and this can be written as k plus 1 k plus 2 by 2 the whole square. So this is equal to right hand side. So see, this is equal to right hand side, and at last I have to write a statement, that is as k plus 1 is true whenever Sk is true. Now this is finished. Now I am going to another question. Your another question is, see, this is a question of factorial. This is a question of factorial, question number 7. This is a question of factorial. 1 factorial plus 2 factorial plus 3 factorial plus dot 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 plus n factorial is equal to n plus 1 minus 1, where n belongs to n. So I am going to represent this statement as Sn. Here factorial can be represented in this way, or there is also another way. We can represent like this: 1 into 1 factorial plus 2 into 2 factorial plus 3 into 3 factorial plus dot 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 plus n into n factorial. N into n factorial is equal to n plus 1 factorial minus 1. Factorial can also be represented as this, like this. So here again as 1, this will be 1 plus 1 factorial 1 plus 1 factorial minus 1. So this will be 2 factorial minus 1. 2 factorial is 2. 2 minus 1, this will be 2, and this will be 1, and this can be represented as 1 dot into 1 factorial. We can represent it like this. Now as k, that will be 1 into 1 factorial plus 2 into 2 factorial plus 3 into 3 into 3 into 3 into 3 factorial dot 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 plus n into, no, not n, this will be k into k factorial, that will be equal to k plus 1 factorial minus 1. Let sk be true. Now as k plus 1, this will be 1 into 1 factorial plus 2 into 2 factorial plus 3 into 3 factorial plus dot 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 plus k plus 1 into k plus 1 factorial. This will be equal to k plus 1, that means k plus 2 factorial minus 1. So I am going to move from the left hand side, that is 1 into 1 factorial plus 2 into 2 factorial plus 3 into 3 factorial plus dot 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 plus k plus 1 into k plus 1 factorial. The preceding term of this is this, so I can write 1 into 1 factorial into 2 factorial 3 into 3 factorial plus dot 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 plus k into k factorial plus k plus 1 into k plus 1 factorial. Now the value of this is this. So this can be written as k plus 1 factorial minus 1 plus k plus 1 into k plus 1 factorial. Now here between these two terms, k plus 1 factorial is common, so here 1 is left, 1 plus, that is k plus 1, so minus 1. So this becomes k plus 1 factorial and k plus 2 factorial, with k plus 2 minus 1. This can be written as k plus 2 into k plus 1 factorial minus 1. So this can be written as k plus 2 factorial minus 1. This is equal to right hand side. Now I will write the last statement, that is as k plus 1 is true whenever sk is true, Now I am again telling you, we can write factorial in this way. Suppose 5 factorial, we can represent in this way, or we can represent in 1 dot. We can represent factorial in these two ways. These are factorial. We can represent either in this way or this way. I prefer this way because it is very convenient for me to write. So I have written I have represented factorial as like this, because it becomes very convenient for me. Now I am going to another question, that is question number your 9. Question number 9, that is 2n plus 7 is less than n plus 3 the whole square and belongs to n. Again I am going to write this as a statement, that is 2n plus 7 is less than n plus 3 the whole square and belongs to natural number. Now for S1, see 2 into 1 plus 7 is less than 1 plus 3 the whole square. So here you see 2 plus 7 is 9, and here 4 square is 16. So 9 is less than 16. So S1 is true. Now I am going to write Sk. This will be 2k plus 7 less than k plus 3 the whole square. Let sk be true. Let sk be true. Let this be true. So as k plus 1, I can write like this: 2k plus 1 plus 7 less than k plus 3, no sorry, k plus 1, k plus 1 plus 3 the whole square. So I have to prove this statement. We know that this statement is true. We know that this statement is true. So I come from this statement: 2k plus 7 is less than k plus 3 the whole square. Now what I am going to do, I am going to add, see, this is 2k plus 2, 7 plus 2 is 9. So I am going to add to both sides, 2k plus 7 plus 2. I am going to add to both sides, k plus 3 the whole square plus 2. Now this is 2k. Now this is 2k plus 9 less than this k square plus 6k plus 9 plus 2. So this will be 2k plus 9 less than k square plus 6k plus 9 to 11. So now this is less than k square plus 8k plus 16, 8k plus 16. So it is automatically less than this. So now I can write 2k plus 9 less than k square plus 8k plus 16. So this will be 2k plus 9 less than k plus 4 the whole square. So I can write like this, to write like this: 2k plus 1 plus 7. I can write like this, less than this I can write as k plus 1 plus 3 the whole square. So if this is this is proved. And I have to write the last statement, that is, as k plus 1 is true whenever sk is true. Whenever sk is true. So now question number 11: factorial n greater than 2 to the power of n belongs to natural number n greater than 4. Remember one thing here, that this statement is true only when n is greater than 4 and n belongs to natural number. So as n, let us represent this statement as Sn, factorial n greater than 2 to the power of n belongs to natural number and n greater than 4. So here in the statement it is given itself that this statement satisfy only when n is greater than 4. So I will test for as 5. The number greater than 4, natural number greater than 4 is 5. So 5 factorial greater than 2 to the power of 5. Let us test it. So 5 factorial is 5 into 4 into 3 into 2 into 1 greater than 2 to the power of 5. It is 32. Because you see here 2 into 2 into 2 into 2 into 2, 2 to the 4, 4 to the 8, 8 to the 16, 16 to the 32, and this is equal to 20 into 6, 120. 120 is greater than 32. So S5 is true. So S5 is true. Now I am going to Sk such that k factorial is greater than 2 to the power of k for n belongs to, not n, here k, here k belongs to natural number. Now belongs to natural number, and the value of k, it must be also greater than 4. The value of k must be greater than 4. So let Sk be true. Let Sk be true. Now as k plus 1 that is factorial k plus 1 greater than 2 to the power of k plus 1. Now we have to prove this statement. As we know this statement is true, so I am going to start from this statement. Factorial k greater than 2 to the power of k. Now I am going to multiply both sides by k plus 1. K plus 1 factorial k greater than 2 to the power of k plus 1. Now this is equal to, this becomes k plus 1 factorial greater than, now see one thing, see, because it is given here that this statement is true only when k is greater than 4 and k is a natural number. So a natural number greater than 4 is 5. So here I am going to place the value of k as 5, that is 5 plus 1. So this will be factorial k plus 1 is greater than 2 to the power of k into 6. Now see, this is greater than 2 to the power of k into 2. This is greater than 2 to the power of k into 2. Therefore I can say that k plus 1 is greater than 2 to the power of k plus 1. Now this is proved. Now I have to write last statement, that as k plus 1 is true whenever this sk is true. This is finished.